I'm Joshua Button. These are my teammates, Andrew Westerberg, Owen Robin, and Stephen Dillage. Together we are Team Major League Cornhole. And tonight I'd like to show you our presentation on the project, the Automated Cornhole Scoring System. Now this is a revolutionary new way to experience the game of cornhole, which is a popular game many of you have probably already seen or played at a sports bar or party or somewhere. And if not, I'll explain it to you. And our prototype board features a built-in scoreboard that'll display the score and update at the end of every turn. So, as bags land on the platform or fall through the center hole. And how that basically works is in a microcontroller embedded inside the board that tallies up the score, and then the board keeps track of where the bags land using radio frequency identification technology, or RFID. And we'll get into more detail about that in a second. So, a quick summary of how to play. Two-player cornhole is played with a single bag and a single board and 8 bean bags. And what it is two players take turns throwing 4 of the bags of their own color at the board. And they're aiming for the center hole, which is worth 3 points for every bag that falls through the hole. And then at the end of the turn, then each player also gets 1 point for every bag remaining on the board. And then the higher score has the lower score been subtracted from it, and that's the difference is given to the winning player, and the first player is to reach 21 points wins. So that's what we had to do for this project. Now currently, most cornhole boards on the market require the players to keep track of the score in their head. And during a party, there's a lot of noise going on, a lot of distractions, people are usually drinking, it's hard to keep track of that. Now there are some scoreboards on the market, but they're all completely manual, and they usually involve a slider with a little pointer that you adjust at the end of every round. So there's nothing automatic like this on the market. So here's a picture of our prototype automatic cornhole board. You see it is a wooden board, and it's set to meet the specifications set by the American Cornhole Association, which is a real thing. With a clear acrylic thin surface, and that provides a smooth playing field for the beanbags to land on. And it also protects the scoreboard and the other electrical components from the impact of the bags because they're hitting this board pretty hard. So that's pretty much the overview. I'm going to go ahead and give it to Andrew to tell you more about what's inside.
Major Westberg, I'm going to talk about the controls for cornhole board. Okay, so in the blue is the Arduino microcontroller, which we use to calculate the score and output the score to our 7-second display. Up at the top, we have an RFID system, which consists of an RFID reader, an 8-to-1 multiplexer, a center hole antenna, and then 7 platform antennas. And also, we have 8 bean bags, and inside of each bean bag, we have 2 RFID passive bags, which have a unique ID. And the way it works is you send an RF signal to the antenna, and if any of these bags come within the vicinity of the antenna, the RF signal picks up this unique ID, sends it back to the Arduino. And the Arduino has an algorithm which was coded by a C programming language, and it calculates the score and sends it out to our 7-second displays. So that's what the LED display is for down at the bottom. And then we have quick button inputs for a reset, and we also have a next round button that controls the game. Alright, here's our microprocessor, the Arduino Mega. We first started out with a PIC-18, but we hated assembly language, so we wanted to go with C language. Plus, with the 2 serial interfaces, we were going to use a reader for the center hole and then a reader for the platform, but we didn't have enough power for the platform antenna. So we stayed with this right here. And we also need a good amount of digital I/O. We use 30 digital I/O for the LED display and then for the user push buttons. Here's our main control panel. Of course, we have a power on and off switch. We have a reset button. What the reset button does, you hit the reset button, it sends a hard reset to the Arduino controller, basically initializes everything and sends the score back to 0. And you also have a ready LED. And what happens if you turn the power on or you hit the reset button, the ready LED comes on and lets you know that your reader's initialized and the board is ready to play. We also have a next round button, which initializes the multiplexer. So when you hit the next round button, shut your center hole RFID reader off and basically switch through each of the 7 platform antennas. And while it's switching through these antennas, the ready light actually signals let you know which antenna is being switched or whatever. And after all the mux scanning is gone, you hit the next round button again, and the green light comes back on. You're ready for the next round. Here's our RFID system. We used a high-frequency RFID system which runs about 13.56 megahertz with 200 milliwatts of power. 200 milliwatts is the reason why we had to have 7 or 8 small antennas, because there's not enough power to actually output to antennas scanned across the whole board. And at the bottom right is the multiplexer with 8 antennas connected to it, and coming into it is the RFID reader signal. I'm going to turn it over to Roland Robbins. He's going to talk about the antenna design.
Thank you. Okay, the center hole antenna, since it's only one of those, it's in this underneath the platform. It consists of 5 loop antennas that are mounted to, hard mounted, it's equally spaced to a PVC tube. PVC tube serves 2 purposes. It gives us a firm platform to mount the antennas. It also protects the antennas from impact from the beanbags coming through. It also acts like a chute to direct the beanbag through the antenna field itself. By stacking these antennas the way we did lose some energy going through it, but we were able to gain a distance of over 5 inches of readable length that the bag had to pass through. So at any point in time, the bag had to rotate or was moving, it would still pick it up. We attached a net to the bottom of the tube to catch the bags as they come through, to sort of keep them in a general area so it would be easy to retrieve when you get ready to go play for the next round. It also kept the bags within the RF field itself so they could be properly read. We attached a antenna matching circuit to the antennas to give us impedance matching from the antenna to the RFID reader. Okay. The platform antennas consisted of 14 9.5 by 4.5 inch loop antennas. They were square in nature. They were also paired up into 7 pairs. If you see to the left, so see the whole platform with 7 pairs of antennas. To the right was one antenna pair. Each pair was connected in parallel to each other. You also see that we have a tag sitting on the antenna with the field lines going around the antenna itself, protecting the tag itself. Power. That was sort of something that came in late in life. We were constantly using power supplies, but then we finally said, you know, we got to get off the power supplies and actually put batteries on this thing. We were able to use 8 2300 milliamp hour AA rechargeable batteries that give us 10.3 volts. The voltage was good to run the Arduino, so we hooked it directly to the power supply. But for all the other components, we had to drop the voltages down a little bit. So we used 2 adjustable voltage regulators. One was set to 8 volts. That would take care of the 7-segment LED display and the LED driver. The second adjustable voltage regulator was set to 5 volts. That ran the RFID reader and 8-port multiplexer. As you can see over on the picture here, you've got both of the voltage regulators and their associated heat sinks connected. Okay, test procedures and reliability. This is where it got interesting. Center hole antenna test consists of taking multiple bags, dropping them and throwing them at various speeds through the center hole, trying to see if we could get it to detect or not to detect. And we would know that it would detect is if you take all red bags and drop them through the hole, one after the other. If you dropped all of them, you should have your total score of 3 points for each bag listed on the display. So as we drop them through, we make sure, yes, we're seeing that. The platform antenna was a little more interesting because we had to take the same color beanbag and place it in multiple places all over that platform, along the sides, edges, and even off the board itself. because we wanted to know can we read on the board for 1 point, and also we didn't want to be able to pick up any bags that lay outside. The microprocess test used the manual controls, the next round button primarily. What it consists of being able to take the information from the RFID readers, selecting which bags were detected, assigning the point values to the bag to determine whether to go through the hole or be on top of the platform, and then run through the calculations and display the score on the second display. We also got a short demonstration we'd like to show you.
A little upside down, but hope you still be able to read it.
Yep. So you notice when the bag went through the center hole, the bags will land on top. We will have bags that will land off the board at the very end and off to the side. They're kind of hard to see. Now, by pressing the next round button, you notice that the flashing LED is going to scan across the top of the platform, taking what bags are there, and it will display the score on the board right here, and it listed 4 points. You add up, you got 3 for the hole. These 2 here cancel out, those 2 cancel out. One red there, 2 blues off, don't give no points. That gives you a total of 4 points. All right, now I'd like to turn it over to Peter.
Now we're going to be going to the project timeline. So August and September were just preliminary months. We mostly just did planning and other things. We went through different designs of what other ways we could do this besides RFID. We tried to think about weight sensors on each corner of the board to see if there was another way to use RFID. Weight sensors were discarded. It was too difficult to determine which bags were on the board. You could detect a bag, but not which bag. October through November, that was the early antenna design. We did a big antenna, loop antenna, around the entire board. We also did the preliminary of the center hole and how we wanted to do it. But we determined that the large loop antenna was just not powerful enough with only 200 milliwatts power, and we could not power the entire board. Going on to December, we finalized the center hole. We decided that was mounting it on a PVC pipe. That was the best way to have a bigger field to pass through. January through February, so when we started the scoring, the scoreboard, we decided we want LEDs. We've seen other designs where the scoreboard is off to the side, but we wanted everything to be inside the board and as user-friendly as possible. And also the platform design was finalized. Then March through April, we started going to assembly. We put everything together. We mounted all these components to the underside of the board. So when you pick up the board, everything is attached. You don't have to have any extra attached to the board itself. And then we also put in the tags into the bags and started testing. Here's our budget. As you can see, most of the money spent was for the multiplexer, the reader, and then the microprocessor. Here is a pie chart of where we actually spent our money. 90% of what we spent was on the RFID, the reading, the multiplexing, and also the microprocessing. The LEDs and the frame were only 10% of the budget and was not much of what we had. In conclusion, our goal of the project was to build something that an automated scoring system that would not have no human error could correct. Also, we know that this is a high-end product, and there's not too many things on the market. There's actually we've seen very few actual automated, fully automated cornhole systems on the market. Also, the one thing we wanted was internal housing. We didn't want any extra parts laying around along the field, wires that trip over from one board to the other. And another thing, the wireless communication for the second board, that was discarded due to budget concerns, time restraints, and mostly just time restraints and budget concerns. One other thing we talked about was where we could improve on the project. One was using, instead of using high frequency, we would use UHF, ultra high frequency tags. They have a more, instead of having to be flat on the board, the tags could be in any orientation, be more likely to be picked up by the board. And another one would be more manual adjustments to the scoring. Say for some reason one bag gets picked up off the board or one doesn't get picked up on the board. We would also like to add another manual input to just click the score up instead of restarting the whole round.
I saw your testing when you were actually putting or throwing the bags on the thing. Did y'all do any testing where a bag would hit the board and then roll off?
Yeah, that actually works perfectly fine because during the actual game itself, only the center hole antenna is actively scanning. And then it's only when you hit the next round button at the very end that it'll actually scan through the platform. So anything sliding across the board during the actual game won't be read at all. That's not an issue.
With the smaller, lower power antennas on the board, solve any kind of fringing concerns you have? But if you're down on the low end of the board near the ground, when you push the next round button, could you possibly pick up a bag out on the head?
We doubt it.
Not with the size, even with the size of the antennas we had, even though they were smaller, they were still large in comparison to what that unit was designed around. We designed around a smaller, about maybe up to 3 inch antenna. So we were really pushing the limits of it.
Talk about accidentally picking up ones on the outside.
Right. By it being a larger antenna, it was able to really have the power it needed for scanning outside. We only had about a 1 inch outside perimeter scan.
Antennas are a lot stronger inside.